Welcome to a discussion about solutions. In order to talk about solutions, you'll want to be able to identify what an ionic compound is and what a covalent compound is, and how you can determine whether something's polar or nonpolar, and then also what a homogeneous mixture is. That last piece is kind of important because solutions are just a type of homogeneous mixture, where we have two substances combined, physically combined, and in a solutions case, we talk about those parts that are coming together as the solute and the solvent. The solute is the thing that you have less of in the solution. So you can think about the solution as being the whole, and the solute is the smaller part, and then the solvent is the larger part. So if we were to draw a picture, we might have some kind of beaker with some stuff, and our solvent particles, there's lots of those. And our solute particles, not as many. Now, you know that what I'm showing you here is not what you would actually see, right? We're imagining that we could actually have superpowers and see the particles on the atomic level. Because with just our naked eye, if we're looking at a solution, we would see a homogeneous mixture, and so we would just see one phase. But this picture helps you understand what's happening at an atomic level. The solubility of a solute is going to increase with temperature for solids and liquids. And you already have some common sense knowledge of this. You may have found that when you were drinking hot tea, you could dissolve sugar more easily than if you were drinking iced tea. This doesn't work for gases. So when the temperature of a solution goes up, the solubility of a gas goes down. And so when we talk about aquatic life, like fish, we get concerned sometimes when, well, not sometimes, we get concerned if, say, the fish are in a lake or a river and the temperature of the lake or the river warms up. Because when that happens, the solubility of oxygen that's dissolved in the water that the fish are relying on, well, it's not as soluble anymore. And so there's less oxygen available for aquatic life, and so fish die. So we get kind of concerned about increasing temperatures of solutions when we're talking about gases. Well, at least when we're talking about living animals. On the other hand, if you increase the pressure of a gas over a solution, this is described by Henry's law, you'll actually increase the solubility of the gas. Now, increasing the pressure for a solute that's a liquid or a solid doesn't really do anything for you. But if you think about opening a can of soda or any carbonated beverage, when you open it, you hear that psst sound. That's the gas that was stored in the headspace between the top of the liquid and the rest of the container, filling the rest of the container, so that it was keeping the liquid under pressure. And the reason it was there was to keep the carbon dioxide that was dissolved in the solution, to keep it dissolved. As soon as you release that extra carbon dioxide and you pour the soda or whatever carbonated beverage you have into a glass, you start to see bubbles because there's no longer that pressurized gas on the surface of your solution to hold the carbon dioxide into solution and keep it dissolved. We'll talk about solutions in terms of whether they are saturated, unsaturated, or supersaturated. And saturated solutions have sort of the precise amount of solute dissolved in the solvent that the solvent can hold. So this is sort of the magical point. So it's the max, we say maximum, but then you're going to think I mean something else later on. But we'll say maximum amount of solute the solvent can hold. An unsaturated solution has less solute. Oops, forgot the less solute dissolved than the solvent can hold. So we're kind of talking about capacity of a solvent to dissolve the solute. And saturated is sort of the capacity, and unsaturated means it hasn't reached its capacity yet. Supersaturated is kind of a weird little thing because a supersaturated solution is actually a solution that has more solute dissolved than it should. Now, you might be saying, that's very odd. That's because this is a solution that has been heated. So we just talked about the fact that the solubility of solids and liquids goes up as the temperature rises. So if you took a solution that's saturated at a particular temperature and you cooled it down, and you managed to keep all of that solute actually dissolved, then you would have a supersaturated solution. So this is a solution that has been heated and cooled, and which has more solute dissolved than the maximum capacity of the solvent. So, what will a question like this look like? Let's consider sodium chloride. At 50 degrees Celsius, hey, they're giving you a temperature here because they're letting you know this is a particular set of circumstances. It's a particular temperature, a particular solubility. It says that at 50 degrees Celsius, we have 37 grams of sodium chloride per 100 grams of water. If the solution contains 17 grams, if I have a different solution, it contains 17 grams of sodium chloride dissolved in 74 grams of water, is that second solution unsaturated, saturated, or supersaturated? Now, to answer this, I like to just ratio the two together. And I'm going to consider my first solution, which is the definition of saturation for sodium chloride under these conditions. And I'll take my 37 grams of sodium chloride, and my 100 grams of water, and I'll just divide them. And that gives me 0.37 grams of sodium chloride per 1 gram of water. And then I'm going to do the same with my second solution. It has 17 grams of sodium chloride per 74 grams of water. And when I do that math, I end up with 0.23 grams of NaCl over 1 gram of H2O. Now, by ratioing these two together, now I can compare apples to apples. Both of these have a certain amount of sodium chloride dissolved in 1 gram of water. And in my saturated solution, I have 0.37, and in my second solution, I have 0.23. 0.23 is less than 0.37, so I can say that this solution has an unsaturated characteristic. If I had had exactly 0.37 grams dissolved, then I would have a saturated solution, and if I had had more than 0.37, then I would have a supersaturated solution. On occasion, you may find that you want to know whether an ionic compound is soluble in water or not. This is particularly helpful for when we talk about electrolytes in Chapter 10. And it'll come up in a couple of other places, but that's sort of the big application place. You will always, when you're asked to decide whether an ionic compound is soluble or not, you'll consult a table like this. And this is called a solubility chart. And it's divided into two sections. My first section is going to tell me generally compounds that are soluble. And the second part tells me generally those that are insoluble. And so I'm going to start down here with sodium carbonate, and as I look at the formula of my ionic compound, I'm checking each box to see if I can find sodium or carbonate. And I see that I have sodium here, and I actually have carbonates over here. And both of these are going to tell me the same information. I'm going to check the sodium box because I see that sodium ions are generally insoluble, and there's no exceptions over here. So that tells me that sodium carbonate should be soluble. And I get the same information if I looked at the carbonate side. The exceptions include group 1, of which sodium is a part. And so even though most carbonates are insoluble, sodium carbonate would be soluble. Next, I'm going to check out iron 2 sulfate. I want to look for either iron or sulfate, and I find sulfates down here. I see that there are some exceptions to the general idea that sulfates are soluble, but iron is not included in them, and so therefore I can say that this is also soluble. Calcium sulfide, I don't see anything about calcium, but I do see some information about sulfides right here. they are generally insoluble compounds. There are some exceptions listed here, but calcium is not among them. And so we would say the calcium sulfide is insoluble. When deciding whether a covalent compound is soluble or not, we use the general rule that like dissolves like. So polar things dissolve polar things, and nonpolar dissolves nonpolar. So these guys will mix, but polar and nonpolar, they won't form a solution. Nope. And polar and nonpolar, you can think of water and oil. They don't mix unless you add an emulsification agent like an egg. Otherwise, you're pretty much just stuck. So how do you decide whether a substance is going to mix or not? You need to decide if the compound is polar by drawing the Lewis dot structure. And throughout this conversation of solubility, we're always, in the back of our mind, referencing that our solvent is generally water. So water is polar. We are looking for substances then that are also polar and among covalent compounds. Let's consider carbon dioxide and formaldehyde. In order to decide whether they're soluble, I would need to draw their Lewis dot structures, which you should be pretty familiar with at this point. If you're not, go back and review that video so that you're comfortable drawing a Lewis dot structure. So there's carbon dioxide. Here is formaldehyde. And what I notice is that carbon dioxide is nonpolar, or we would predict it's nonpolar, and we would predict that formaldehyde is polar. And based on that information, we would say that it's likely that formaldehyde would indeed be soluble in water and that carbon dioxide would not. Why do solutions form in the first place? Well, we might want to talk about kind of the energy of solution formation. You have to pull apart solute molecules from other solute molecules and solvent molecules from other solvent molecules, and then you kind of need to get them all mixed together. And you need attractions between your solute and your solvent molecules to develop. And once that happens, once you've overcome the attractions between solute particles and between solvent particles, and you've made solute-solvent attractions, then you actually have a solution. If you add heat, or you stir, or you subdivide your particles into smaller bits, then you can make the process go faster. Doing those things doesn't actually change the amount of solute that you can dissolve in the solvent. It just speeds up getting the thing actually dissolved.